Our today's guest is Edward Kmett, a self-proclaimed genius consultant and a mastodon. You said it.
Sure, I guess I did it at one point.
And a mastodon of the Haskell ecosystem. If you ever had to modify a deeply nested structure or map over both left and right parts of something, odds are you have used his libraries. He has encoded a lot of stuff for us to enjoy, and he did it in style. Edward, welcome to our podcast. Tell us, how does it feel to author so many libraries used everywhere from like academia to industry?
It's really weird. I never really planned on it. I mean, I sort of did. I came into the Haskell ecosystem and I looked around. And at the time, it was just like right after they released Cabal. So they had just gotten to a point where we had a package management ecosystem, right? Like previously, you get up to about 2006, 2007, there really wasn't a good way to build on other people's code. And I started just trying to write down all this category theory stuff that I was hearing about, mostly through the Haskell channel, and trying to make sense of it. And I just kept building a bigger and bigger library worth of category theory stuff. I took over one that had previously been maintained by somebody else. And it just kept like metastasizing into this larger and larger thing. And then I think, Connell Elliott actually reached out to me and said, hey, I would really like to use comonads out of category extras, but there's like 300 modules or something like that in there. And there's no way I can bring myself to pick up that much of a dependency. And Russell O'Connor and some other folks were trying to convince me that maybe I should break this thing up into pieces. And so I did it. And somehow, I don't know, it destroyed my productivity. This was the first of like several such blows that I took. Like I broke it into like 50 different packages or 25, 30 different packages or whatever. And I just couldn't really make rhyme or reason out of it. Eventually I found a way to fuse some things together and I got back into a productive workflow. Then I added more packages and it just became a bigger and bigger thing. There were like 2 or 3 of these, like, oh my God, I was stretched to the breaking point. How am I holding all of these pieces together and dealing with all the people sending me patches on GitHub? I think there was a point at which I was the 5th most active user on all of GitHub, and the 4 people above me were companies. It became very bizarre. But there were 2 audiences when I really started doing this. Like in the Haskell community, there were like the academic folks who weren't being paid to maintain anything, and the industry folks who'd maintained the wrong idea forever because, gosh, they needed it. And there was nobody who would just like write something down, take the stuff that was like really low-hanging fruit, not academic, not publishable results, just get it from academia into practice and like agree to maintain it for a decade or so. And now it's a little over a decade later, and it's largely been maintained. Now it's mostly on the back of other folks, Ryan Scott and those folks who like just kind of keep the lights on when my attention kind of gets distracted and I go elsewhere. And so I will admit it's kind of weird because I feel like it should eat more of my life right now than it does. But because of that long series of accidents, which ended with a big cancer scare where I made sure I had a bunch of clearer successors for a bunch of projects, didn't quite end there. But like that was where I think a large chunk of the downshifting in time consumption came in. I'm somehow able to like hold down a day job and help out with other causes and do things. So it's a little overwhelming at times. I will confess.
So I guess none of our listeners will make a nice big library anymore and then break it into 300 pieces. Actually, I remember
Well, I went the other way at the end with Lens. Data Lens already existed, so there was a tiny little library, and then there was Lens Family, which had the new idea of a different way to encode lenses. And I just wanted like a one-stop shop with all the stuff in it. And since the broken out version was already there, I had no reason to go after that approach. And so Lens just went back to the big monolith, so in many ways, I just kind of reverted to my original latent ways.
Right. That's
my apologies for the build time, everyone.
Yeah. I wanted to say that, and then MicroLens appeared, right? I know a lot of people are using.
I can't use it. I'm sorry. I use prisms.
Of course, yeah.
And so since I use too many things that like, there's no way I can use micro lens.
Actually,
so I'm sorry that some people might,
actually that's a cool thing, right? Like, because that's a cool thing to discuss. Like, and I have it as questions a little bit further down the line, but does it? So when you have like an abstraction that you really like and you know problems for, and you apply to, as a solution to problems you don't know if it will necessarily apply, do you feel some emotions about people like not using this abstraction and instead like rolling their own, or just not seeing kind of
let's look at like what happened with prisms as an example within the lens library, right? We had some idea that there should be some kind of like inverse of a lens, something that like works with like case matching or something like that. We kind of figured it out. Like I've talked about it in previous podcasts and other forums and stuff like that, so I don't really need to rehash that story. But it was like, it took us a long time to find the right theory for it, then to find the right encoding of it. I think the first talk I've given on lenses used an earlier encoding of them, and then we found the right way to talk about it later. But then, somebody wrote a library. I think it was called ESON Lens or Lens ESON. I don't remember which one. Whichever one's the one that you would expect to reach for. And it was like, it tried to use lenses, but it mangled the laws. And it really like stuck in my teeth of like, this isn't really using lenses. This is just kind of like trying to make the types fit, and it doesn't work. And so we sat down in the lens channel, and somebody else contributed the initial sketch of it. And we just wrote down, okay, well, JSON is a big sum type. Let's just write down all the cases. And that was it. That was the entire freaking library design. And now all of a sudden, lens went from being this thing that could work with state to this thing that would work with, well, if you happen to be building some kind of microservice, what do you work with? You take in usually some CRUD pile of JSON or XML or whatever the heck it is. You smash it up using a bunch of state that happens to sit inside of a bunch of maps or whatever that are in your state. And then you spit out another big document or something like that. Maybe you interact with a database or two along the way, right? This is the life of a CRUD developer. And the fact that all of those pieces, like working with the records, working with the JSON that you're reading, working with the XML that you're emitting, all fit into the same vocabulary, I think went a long way towards Lens getting as broad adoption in industry as it did. If it was just this cute little theoretical tool for how to access fields, I don't think anyone would have cared.
Right.
And adding like the other little trick that was, you don't have to import lens in order to define lenses, like enabled it to sneak out into the ecosystem in a way that a traditional Haskell library couldn't, at the expense of my email being filled with hate mail for writing non-Haskell code for years. It finally settled down after people just accepted it as part of the ecosystem, but it did take a good long
time. And that's because like you don't wrap. Sorry to
no, go for it.
Maybe a silly question, but what do you mean when how do you achieve it? Rather, how did you achieve this sort of openness that something can be a lens, and then you can still
a lens or a traversal or whatever, because there's no new type there in that way, right?
Yeah.
Now optics turned around and came along later, and Gundry and folks tried to make that more opaque. Right. But then you don't get the beautiful nature of being able to pun the dot from Prelude as both function composition and field accessor. You don't get a lot of the things that make lens pretty.
Right.
You don't get the clean interop between all of the different optics, even ones that you didn't even know about. They just become things that are given to you kind of by common sense properties of category theory. Now, I did point out at the time we did Lens that you could do profunctor-based versions of this, and we had to adopt the profunctor-based encoding, at least for prisms. But because we didn't want folks to have to incur a dependency on the profunctors library or on the Lens library in order to write lenses and traversals, we wound up encoded with the sort of weird half mix of Van Laarhoven lenses and profunctor lenses, which then let optics kind of come in and say, hey, look, we did the profunctor story. Well, great. Yeah, I'm glad that we told you how that could work. And then they stuck it in new types, and I lost interest.
Right.
And I understand it gives slightly prettier error messages. There's some things that you get out of it. But I think the research vein of, all research on optics stopped the moment things got fossilized into that, right? Like the notion that a lens to me as a cofunctor has nothing to do with profunctors whatsoever, really, is something that you would never see if you're squinting at it through that lens. No pun intended.
That's actually a really, really insightful thing. Like, because a lot of us in the industry have this mindset. Oh, okay, let's wrap everything in a new type as soon as we can, and then just kind of push the kind of make it into a black box, right? Like, okay, maybe I have some fundamental properties, but I don't care because I'm writing industrial code and I just want to wrap everything in a new type. So what you're describing, I'm not sure if it applies to like the industry, but it's a beautiful case against the new type, I guess.
Well, in this particular case, like Haskell doesn't really have subtyping. It sort of does. Classes have a notion of subtyping between them, right? Constraints have subtyping, right? You have like an implication in the category constraints. And so the only way to get subtyping is you can say, well, if I have a free variable A, then I can instantiate it, right? It subsumes int or something like that, right? I can use that way. And the other way that I have that involves any sort of subtyping is I can say, well, if I need something that's a foo that's eq, I can pass it something that's ord, right? Because ord is a subclass of eq. And those are the only two mechanisms that I have to really express subtyping, where I can pass a thing like covariantly or contravariantly in a given position, right? Either I can return it covariantly or take it contravariantly. And so the lens trick, right? Like I let you basically pass me any function with like any choice of functor that you choose, and then the constraints on that function are selected by the combinator you use it with. So you express the lens once, and then what happens is when you stitch them together, the constraints get unified, right? Or unioned to roll up to the bigger set of constraints that you've incurred. And so that just sort of naturally falls out that you get lens composition. Composing a lens with a traversal gets you a traversal, all that kind of stuff just works across the board. And it's just exploiting the only notion of actual proper subtyping that we have. Without it, you have to express some kind of lattice by hand and then use your own machinery to kind of get that to roll up and ball up into the answer. And I don't know, it was this sort of, when you go to view over a list of, like a traversal or something like that, you wind up asking yourself for a monoid for the summary or whatever that you're producing. That judo flip move comes explicitly from lenses opening up their guts. And optics can't express that pattern. Now, the folks behind optics would turn around and say that, it's a safer library because you don't have these weird like monoid constraints coming out of you out of nowhere. But my primary goal for Lens was to build a library for me with like warts and everything and all kind of included, in that I wanted a vocabulary I would still be using a few years later. Like my goal was 2 years later. In 2 years, I still want to be using this library for fiddling with field access and stuff. And now we're 10 years later and it's still going strong. There's a whole cottage industry of folks exploring lenses for category theory, for things that have absolutely nothing to do with our computer science uses. There's folks using them for like talking about derivatives of functions. There's folks talking about using them for
like actual
Bayesian
numerical
belief updates.
Actual numerical derivatives or
numerical derivatives.
Nice.
Yes, you can actually view them almost like a lens. And if you actually take the proper cofunctor encoding of things, you can actually make that rigorous. And there's a bunch of things that we can turn around and say. Now, the problem is, of course, I can't really talk about cofunctors in Haskell. And for those following along at home, cofunctors are not contravariant functors, despite what some people in the Haskell community may have abused terminology to refer to them as. They're a different thing, and it took me a long time, but I do finally agree that that's actually the right term.
So yeah. Which arrows do you flip in functor to get a cofunctor? Because actually, I had a very, very nice experience as I think in like 10 years ago or so. There was the talk about functors. I don't remember who gave it, but they had two types of arrows, right? One that goes from like A to B is like, I don't know, universe one arrow, but the one that kind of actually is the functorial arrow was signed with like was denoted with a different notation. And
I used a little fish hook when I did my all about
yeah,
Comonad's talk.
yeah,
That was
yeah.
literally the first Haskell talk I ever gave.
Maybe it was your talk.
It was my talk.
Oh no. Sorry that I forgot it was your talk. That was
it's all
very
good.
cool. That was very cool.
There's a Jeff Newbern had written an article on all about monads. And so I kind of riffed on the context of all about monads because he was going to be there at the talk I was giving. This was for the first Boston Haskell. And so BlueSpec opened up their offices to us. And so we descended on them, I think in, I've forgotten where the heck they were in Boston, in the Boston surrounding area. So we descended on their office and I took over their conference room or whatever and presented this, and then Shay Harrison presented another thing. And that was how we started Boston Haskell. We ran that for 5 or 6 years, I think. I lost track of exactly how long Boston Haskell ran for. I believe it's back running again.
Yeah,
but I haven't seen any of the new videos.
Before showing off the arrows, I just want to thank you, well, all of you, for Boston Haskell, because I mean, I was living in Eastern Europe and I couldn't. First of all, there weren't a lot of books like on our bookshelves or online about Haskell. And second of all, just having like video content was it was a very scarce thing to find. So like, I think I watched it all, everything that's on YouTube, and that was really cool to learn how.
Yeah, you can really thank/blame Shay Harrison for most of that, getting it off the ground originally. Actually, you can also he's the reason why I started blogging about Haskell. He convinced me after I hired him to do defense contracting stuff for me for a while that maybe I should just start blogging all the weird stuff I was rambling on about at lunch. And so I started Comonad.com and blogged it, right? So the Comonad Reader, that website was named after the Monad Reader, which was a sort of faux scholarly journal, like not quite scholarly journal quality thing for just like sharing like user level Haskell kind of stories and tips and tricks that Shay started. And so I named my website the Comonad Reader because I had been doing all this Comonad stuff right at the time, right? And that's where my blog came from, which I haven't updated in a painful long time. I started writing a bunch of stuff on the School of Haskell, and then they took that down, and I never really got around to finding another venue. I should probably start blogging again in my endless amounts of free time. So you asked a question about cofunctors, and I kind of mentally put it in a parking lot. So I apologize. I'm going to try and draw this on my fancy little whiteboarding setup here. And so this might work better for the folks who are following along on YouTube, but the podcast folks, I will try to be evocative as I speak. Okay, so what is a cofunctor? So a cofunctor maps objects from one category to objects in another category. This sounds an awful lot like a functor so far. But then it maps arrows in the target category back to arrows in the source category. So if this was S over here, and you gave me a way to turn A's into B's in the target category, I will get you the T here, which is the image of if I were to change all the A's into B's or whatever over here, or however I'm going to meaningfully talk about this, how I will get the object up here. And this has the property that if I send it identity arrows, I come back to where I am. If I compose these arrows, I'll come back to the composition, and it doesn't matter the order. If I had, 3 of these arrows or whatever here going A, B, C, D, whatever, and I went to compose them in different associativities, I would get the same answer, all that, right? So it has the usual shape of a functor, except for the fact that the mapping happens in the target category, not in the source, not in the category that you're coming from. So it is the opposite in this respect. And then you can get fancy and convert this into a story about monads in the category of spans and comonad. There's a way to encode this that actually makes one of these the dual notion of the other, which folks who are better at category theory than I can articulate. But what I like about it is that if you dip heavily into the language of poly, which is like this category of poly, polynomial functors that David Spivak likes to talk about, and we use a fair bit at Toppos, then you can start looking at a lens in their vocabulary as a functor from sy to the s to ay to the a. And this is basically store comonads with, like, this is more or less the store comonad, or every comonad gives rise to a category, and then you can play with some interesting structure here. But this looks like exactly like a lens with the get and set laws intact. Or if you replace this with a one object category that's a monoid, this becomes like a monoid action. And so you can start expressing monoid actions and lenses and a bunch of other things using the same vocabulary. And the reasons why I care about this sort of thing is, like, if you look at lenses, like, it's kind of frustrating to me as a user of lenses that I have to be able to, like, the get function has to be like total. The set function for a given s and an a, like, like if I'm going to give you back an a here, right? Every a has to be able to be obtained out of here. And the reason is because when I go to put it back in to s, when I get out of this result, I need to be able to get you the a that you put in. So I put in one here, it needs to be able to come back out. And if I don't have that property, and I realize this went very poorly for the audio only followers, so I will try to refrain from getting enthusiastic and scribbling. So as a result of that, like, this sort of totality, that, like, a lens has to be sort of equivalent to having, like, I could break S into pieces, the A that I'm looking at and all the other stuff, this complement, right? And then I can take this thing in the complement and put it back together to get my original value. That's really what a lens is. If you like another way of looking at a lens. That encoding means I can't. What does it mean to relax the lens laws, to, like, allow get versus set to be, weaker? Well, maybe I say that, like, the embedding from S into the pair of A and C, the complement. Maybe this isn't an isomorphism. Maybe it's just a section retract pair, or it goes in the other direction, and that lets me relax either the set get or the get set laws. There's a whole BX community, like bidirectional transformations community, that's been devoted to this, except they relax the third law, which is the set law. But if you look at that, really, if you had an encoding of lenses as cofunctors, then you'd be able to just sort of carry the set law, and everything else would be a special case of, like, just choosing the target category, the thing you're looking into for your cofunctor. But then all of the things about Bayesian updates become, hey, look, it's not that you get the value that you put in when you set the second time. You get the composition of the arrows and we have a constant arrow when you happen to be working in a Cartesian category like Haskell. And so that's why you get the set law that you do in Haskell. But, like, you get sort of a map law that's sort of universal, which corresponds to the way that the lens library encodes things. I don't know. This is sort of the things that keep me up at night when I start thinking about lenses. I found a nice encoding using the constant complement encoding of lenses just the other day for Rust, to get a version of Rust lenses that actually have decent type inference. I posted it to Twitter, and with a Godbolt link to actual code. But I don't know. But it's still not the cofunctor encoding that is the one that rattles around in my brain as the true encoding of a lens. An example would be, maybe I have the ability to convert, date times into, like, get me the second hand, right? Like the number between 0 and 59 or whatever that is, the seconds for a given date. Now, the problem is that I need to be able to give you any number back from 0 to 59. But then leap seconds exist. Positive and negative leap seconds exist. And so given the date that I am looking at, I may or may not be able to give you a 60th second, or only up to 58th second, and have that actually hold with all the lens laws. So that would be kind of tedious. We usually just say, YOLO, screw it. We just relax one of the lens laws, and we just work with a slightly improper lens. maybe a better encoding is that you go from a date over here to giving a prism that like matches the subset of those things that are valid dates, and then turns those back into like the raw number of seconds since 1970. But there's various encodings of this that like kind of flip and put the problem on the other foot. And I guess I get most sad sort of in that microlens story when you've deliberately, in the pursuit of a slightly more minimal interface, cut yourself off from the identified solutions to the problems that you've created for yourself. But then again, I'm the fact that lens is as large as it is, I don't blame people for wanting to shave it out of their build times.
That was a very nice example. By the way, with the date time, and it's for me it's kind of difficult to keep it all in my head at once, especially with the cofunctor story. I kind of understood most of the stuff that you said, and yeah, but I naively, like very very naively, I wonder, would dependent types help with this particular thing if you could say? But I guess it's also cheating, right?
There are encodings of lenses in Agda and whatnot, right? And the real question is do you carry around the laws, right? And I think this is really where my frustration comes from with like the folks who went off and did a bunch of profunctor lenses, not to kind of poke at it, but it was like they left the lens laws on the table because they weren't intrinsic to the profunctor encoding of lenses. They were something that you bolted on. The profunctors were the only thing I could really talk about that gave me, hey, look, I've got a type for what I'm coming in at and what I'm coming out at, and this mapping between the mappings of those types, right? And that's what a profunctor gave me. It wasn't that was the right like underlying notion. What I really wanted was that a lens was, like given some kind of indexing category that's probably discrete. I've got two functors down to set. Let's call them S and A. And then I have, like a family of morphisms, phi. Am I off the screen here? I apologize. I'm right at the edge. I hope this makes it through the format that you're going to use online. From that, like SI is isomorphic to the product of like A and C. These are AI and CI. So I got this little functor, like this little mapping that goes between this. And then when I go to compose these things, I have a different lens here, and it has its own indexing category. I want to like compose by some kind of pullback or something like that. Give me the subsets of I and J such that A and U map to the same object, and then this composes to get me the new indexing type. And that's what unification does. It does this thing, but in a way that associates in a way that doesn't happen in category theory. And then you can talk about like how this composes with another set structure. But this works for lots of these different kind of like Cartesian monad like things. It looks a lot like a Baroni T-span. There's all sorts of fancy category theory-ish nonsense I can try and encode this into. And I apologize because this was terrible category theory and it was also terrible code. So it was just a sketch of the idea. And again, it probably didn't come out at all for the folks who are trying to follow in your podcast. So I'll try to refrain from this things like crack now that I have this ability to draw.
Right. Yeah. Well, I mean, I will say for the engineers listening that whatever we like, for example, I had like a bunch of thoughts about the example that Edward just presented, but while if you think about it, if you're going to try to naively constrain the totality, with a new type or even with a dependent type, as far as I understand, you will lose composability, right? Because you will have to parameterize early, and then your resulting object, which will be able to get the seconds out of a date time, right, it just won't be like a lens anymore, right? Because
you get sort of messed up. I think there's a couple options of how to encode this. Like you can build a very nice dependent-ish looking lens in Agda. You can also just turn around and let them float like you do in Haskell. Like the real problem is that I want that pullback like thing, this way of composing these sort of these like groupoid like interpretations of lenses, where I want to compose these like this structure with this other structure wherever the types agree. I've got this bundle of arrows and this other bundle of arrows that may or may not connect, and it's only the ones that connect through that actually make it through to the whole end to end, right? If I apply the first lens, the _1 lens, and then I apply the second bit lens, I will only work. This will work. The first one worked for all pairs, but now it will only work for pairs where the second where the first element of the pair is integer. And so you like this pullback is sort of doing that refinement work, making sure that your lens continues to apply. Now it's, instead of giving me only one direction forward and one direction back is being selected out of this, we're actually letting them all through. But I can't talk about that. I can't control generalization when that happens in a language like Haskell. You could maybe come up with a language that had like some kind of binder syntax for a lens that explicitly dealt with generalization and like did it at the right times in order to let you build the lens and keep kind of passing them around. But that's not Haskell, and that's not Agda.
All right. I mean, this is a part of
the reason way in the why weeds, I have to admit.
why I love podcasts with Edward, because you listen to them first time, you understand something, then you listen to them second time, third time, fifth time. Perhaps you read a bunch of textbooks along the way, which is, by the way, which brings me to another topic that I really wanted to discuss. I know you're not a huge fan of going very deeply into autobiographical stuff. And I got this knowledge from rather old, but in my opinion, legendary talk that is called Stop Treading Water. Sorry, yes. Which is, I think for me was perhaps even the most influential talk by Edward, and I hope that you will forgive me for not emphasizing your more technical ones. But basically, there you mentioned, right, that you weren't like born into a family of mathematicians and was drawing arrows in the sand since you were 3 years old, right? You somehow got to a place where you can fit all these abstractions.
I had like one uncle who was a computer scientist. No, not really a computer scientist. He was more like a self-taught like electrical engineer, but I thought of him as a computer scientist, right? And so he kind of showed me some like basic 7400 series TTL logic kind of stuff, and this led into some like little robotics projects and stuff like that caused a bit of a house fire when I was a kid, which then forbade me from soldering. And so that's why I kind of became a software person. Like I was just like, I'd been going down this road and then lit the house on fire, and then mom said no. And so after that, I stuck to not opening up my computers, and I just kept programming. But again, like the programming was, I started up, like I grew up like until like third grade, I was in downtown Detroit. And my mom didn't really want me going outside and playing with the kids in the neighborhood. It wasn't terribly safe. And so she was happy to have me like plugging away on the computer. And then we moved out to the suburbs, and I had like transmogrified into like the computer kid or whatever. And so in third grade, I lied and told the kid that I had written a disassembler for the Commodore 64. And then he didn't believe me on a Friday. And so I went home and hacked it together and actually made it sort of work, and slapped down a disassembly of the Commodore 64 basic ROM on his desk. And he believed me, which is good because it was totally freaking wrong. And I spent the rest of that year trying to make that thing right. And that's how I learned to program, was through writing this like thing almost on a dare over a weekend, and then using that basic ROM or whatever as like my Bible for like how people must write code. And I didn't realize that this thing had been kind of like crapped out by Bill Gates himself back in the day. and then optimized to fit in this Commodore, like where they were just at the edge of things. And so like the last byte of the sign table is the first byte of the next function and stuff like that. I just thought that was the way everyone programmed. And again, a lot of my most outstanding successes have come from misunderstanding what is expected or what other people do, right? I came into the Haskell community. I assumed the entire Haskell community was full of category theorists because I was sitting on the Haskell IRC channel and Cale Gibbard was there using category theory I didn't know to solve computer science problems I didn't know. And I'd just done a master's in each of these freaking things. It was really frustrating to me because I just hadn't had the context. So I just assumed this entire community was made out of folks like Cale. And little did I know that all he did was read papers all day. Now he actually is gainfully employed in doing stuff, but I'll never lure him away from Ryan. Yes.
Well, I mean, I think that the most, I guess, applicable thing, hopefully even actionable for many of us and many of our audience, many people from our own audience would be to maybe not even learn like how did you go from kind of, hacking on BASIC to drawing arrows, but more. And by the way, not only that, I mean, we're going to talk about like programming and languages and stuff like, but kind of like, when did you do that? And like, how is it possible, for example, to be like a full-time engineer, I don't know, writing in Python or something like that, and at the same time kind of build up intuitions or maybe build up some hard skills, right? Because like doing, for example, category theory and coding stuff, it requires hard skills as well. It's not just about understanding.
Yeah. So this is where I think the right PC, the answer that everyone wants to hear is the one that says, "Oh gosh, you could totally do this if you just worked harder." And I don't know that is necessarily always just true. There's a lot of luck and a lot of picking the right problems and a lot of deliberate, almost sort of defocusing on what nominally should have been my priorities at given times that went into getting me to where I am and what I do. Some of it is like sort of calamities that happened in my own kind of personal life. Like I went off and made and lost a lot of money trying to build a phone company / ISP in the late 90s through early 2000s. And I wound up rather crushingly in debt at the end of it. And so I spent basically a year on my now wife's couch doing nothing. And she eventually started like circling help wanted ads in the paper and just subtly leaving them there, And so I went and decided I was going to go back. And so I'd done one semester worth of college, like right out of high school, left because Ford offered me what I thought was a lot of money, wound up suing Ford over a bunch of other stuff, and wound up taking that money and helping to build a phone company, which is its own drama. But the end of that was this, hey, look, and now I'm broke. And I've also had to fire all my friends, so I don't have a social circle, which didn't end so well for me. But I had a work ethic, and I had the fact that I had been doing graphics and some game dev programming and whatever during that time while running the phone company. And it was really just, I didn't want to turn into a suit, and I like really loved doing the graphics stuff. I found my way into this community called the Demo Scene, and they had all sorts of, I don't know, neat data structures and algorithms. And so I learned data structures and algorithms kind of from first principles in order to try and figure out how to fit things into demos or help other people fit things into their demos. And a large chunk of that was like the visual payout of seeing something render, right? Like I could get a very tangible result out of learning some linear algebra or a little bit of diffie-q or just playing around with what is inverse kinematics really? Oh, that's what it's for. And then I can get the thing to actually grip the wall or whatever, whatever I'm trying to do. Those pieces felt really real to me. And so when I got the opportunity to go back and collect degrees, it was, I'd been a CTO for several years at that point in time. No one wanted to hire a CTO who didn't have a formal education. And just doing that bender through academia helped me fix the resume imbalance. Right. This was right after the .com crash, and then the sort of general internet crash that came afterward, the ISP crash that came in like a year or so afterwards. And no one was going to hire me after that. Like, I wouldn't believe I'd stay for anything low level, and no one wanted to take a risk on a CTO level kind of person who didn't have a formal education, who couldn't immediately point to their last thing as a success story in the desert of nobody having a success story. So that's when I went off and kind of hid in academia and collected a bunch of degrees. And the problem there was I just didn't understand the game, right? Like, I did my undergrad that year. I did a master's in math the next semester, but I didn't publish anything. I didn't really get into like what it takes to be a proper academic. I was getting ready to go do a PhD, maybe over at Harvard or whatever, with Greg Morissette and the group that I was just finishing up there. And that was going to move me to Boston. I got an offer to do some defense contracting out in Boston. That's how I got to Boston. And then the Morissette's group over at Harvard wound up going a different direction than I was terribly interested in. So that application process kind of died on the vine. And I just did defense contracting and then finance and what have you. But so where did the math come from, right? Part of it was that I had this ability to just stop everything and go off and do an incredibly intensive academic bender for 3 or 4 years. When I was 29-ish, somewhere in that late 20s, I got to just stop, disconnect from the world for 3 or 4 years, and add a pile of student loans because I'm American to my already undischargeable debt because I still owed things through the bankruptcy, and then somehow emerged from the other side reasonably sane and having found Haskell. Because I didn't find Haskell until the very end of that process. But having done this weird Frankenstein math degree, which was a little bit of everything that was offered by the university, I could make it through McLean, which is really the only real inroads into category theory that anyone had at the time. Now there's much kinder, gentler introductions like Emily Real and folks and the Hot Book and all that kind of stuff provide and Leinster and Audi. There's a bunch of better references now than there were at the time I was trying to learn category theory. And I still can't say that I do category theory terribly well. I speak with a very strong Haskell accent. Like folks at the Toppos Institute almost make fun of me on it. They're very kind about it, but I see it as such. So I don't know if that directly answers your question, but it was how did I get there and how do I do it? It was really a series of these fortunate coincidences, these opportunities that were put in front of me that I kind of ran away with or abused, rather than something that gosh, here's a good piece of general actionable advice that everyone in your audience can go off and take advantage of. Just find 4 years where you don't need to be doing anything. You got those right?
Well, I mean, to be fair, it doesn't really getting. I mean, I don't know too much details about how in states bankruptcy is handled, but I could imagine that it's not the most pleasant experience. And from what I think that what is really inspirational is that okay, how I thought your story went. I thought that you made a phone company, then it succeeded, then you sold it, and then you were okay, now I'm chilling for 4 years, and then you emerged drawing arrows. But your actual story is way more inspirational.
My financial situation went like this, and then created well below zero here, and then I dug myself back out. So I'm still not worth what I was at the peak of that, but I'm doing pretty well.
That's cool. Well, since we're talking about kind of life and stuff, so you mentioned Toppos Institute a couple of times. Can you please tell us a little bit about what it is? Because last time I heard you were doing fintech stuff and selling monoids, I think.
So that was when I was at Standard & Poor's, S&P Global Market Intelligence. So at S&P Global Market Intelligence, we wound up, how to put this, I had given a talk at Boston Haskell, of all things, on reducing big data sets in parallel using monoids and groups and weak algebraic structures. And nowadays, this is just the thing. Everyone does it. But at the time, it was a fairly novel concept. This was probably 2008, something like that. And so Paul Cristiano and Runar Bjarnason were in the audience. They wrote the book, whatever it was, Functional Programming in Scala. And they were over at S&P Global Market Intelligence / Clarify. And they had just gotten to a point where they were trying to replace their portfolio attribution and factor backtesting engine. And it led to, basically they wanted to replace it using my like Haskell library, but they were working in Scala. So they just ported it to Scala. And this was wildly successful by the company standards. And then they brought me in as a consultant because they got in a little over their head. And then later on, I just kind of stayed getting paid my consulting rate. And that helped me dig myself part away out of that hole. So I was there for several years. At the tail end,
this is also Ermine time.
Yeah, that's what we
well,
did.
right?
We did Ermine right after that. And Ermine was less successful, but like still was used for lots of financial reporting and stuff like that, like across the company. It wasn't like the slam dunk that was the portfolio attribution engine. But it was enough that like, I don't know, the company like basically viewed functional programming as could do no wrong. And there was this huge honeymoon phase. And then, I don't know, like several years on, I had a big cancer scare. And that led to me, they were very kind about it. They just wanted me to like go off and do research and whatever, whenever you get around to it. And I just wanted something to sink my teeth into something. And so I like, I don't know, you can think of it as like I upped the annealing temperature on my world state or something like that. I got very uncomfortable where I was, and I landed at a company called Digital Asset doing, working on the digital asset modeling language, DAML, which is a blockchain-based programming language. I made that very pretty and Haskell-y, and then I left about a year later. And it was really, I don't know, it was just kind of a poor fit. Working internationally, it wasn't working so well for me. Most of the organization that I was working with was in either Switzerland or in Australia. And as the American, I was in the worst of all time zones to possibly be working with a team split across, I don't know. And so I landed at MIRI afterwards, which is the Machine Intelligence Research Institute, which is a very polarizing thing on the internet. You can say things to people and they will either love you or hate you about it, for, I don't know, deigning to care that maybe, it'd be nice to have somebody like reasoning about AI safety at some point. And that supposedly carries around with it like lots of connotations about what you do or do not believe. But so I was at MIRI for 3 or 4 years. Just a little bit over a year ago, I left. And while I was still at MIRI, Toppos was getting off the ground. So you were asking about Toppos. And so the Toppos Institute is a nonprofit sort of devoted to category theory, where the main focus is on like trying to use category theory and math to like empower like the betterment of society. It's not, like, let's just do more category theory for the sake of category theory, but let's try and figure out how to like put it into practice. Like John Carlos Baez is a bunch of work on like how to merge different experts models. Like if you've got like an epidemiologist over here and you've got a person who's a specialist in public policy, you can start using pre-sheath models to start reasoning over world states in which like all the things that they believe are mutually true or what have you. And then try to build models that are just sort of jointly better than the models that you're getting out of either one of these things. So that maybe next time there's a pandemic, you don't turn around and start saying, oh no, people don't need to wear masks just because you're trying to preserve masks for first responders, and then have like 8 months later, nobody believes you when you say anything because they always assume that whatever you're saying is because there's some ulterior motive. Like those kinds of things, right? So Toppos has been working with a bunch of epidemiologists actually to build models that are sort of bigger, better joint models that kind of share pieces. I think there's a workshop being run next month with like something like 40 epidemiologists or whatever trying to learn how to use algebraic Julia and the tools that Evan Patterson and Sophie Lipkin have been building. So that's an example. And there's still some other general interest in like how do you do the work on poly. I talked about cofunctors earlier. That encoding of lenses kind of fits into other Toppos work. Valeria De Paiva and her work on sort of corpuses of like trying to track information about what is like an ontology, so you can actually like cross-reference documents that reference things in the category theory space, like basically trying to get an ontology out of NLab, supporting NLab itself. All of those things kind of fit into Toppos's general mission. I think 51 papers last year. Don't quote me on that, or maybe it was 51 videos. I'd be a better PR person if I had the numbers straight in my head, which one was which. But I wasn't actually planning on being a PR person today. So those are the kinds of things that Toppos does / styles into. So that's a nonprofit that I work with. I work with them. I work with the Haskell Foundation. And then I work for Groq, and I do some work with Enso and a couple of other smaller nonprofits that I consult for.
Whenever I hear that someone is doing interdisciplinary stuff, I'm already a fan, and if it's done in a socially conscious way, it's even better.
I think interdisciplinary is you need to have somebody who's an expert in both X and Y, not just an expert in X and an expert in Y kind of vaguely on hand. It's very hard to get get the ideas across the divide without some sort of Rosetta Stone.
Absolutely. And also this is a very dangerous, interdisciplinary stuff is obviously the future. So I think so. But there's a very dangerous thing which I call like analogy fallacy. It's very scary because you can just exchange analogies with an expert from another field, which don't really hold water, like when put to rigorous testing. Did you have experiences like this?
So much. I don't want to name a chain, but yes, this is a very common. As someone who's been a consultant for a good long time, you get this a lot, especially when you're dealing with domain experts who don't really want to explain their domain. I think it's really like an example is like, I'm working at Groq right now and we're building AI chips, right? Like I don't know how much you know about Groq or anything there, so maybe I should say a few words.
Probably.
I'm the head of software over at Groq. Groq is a silicon manufacturer. If you're familiar with Google's TPUs, the guy who designed the TPUs for Google, the guy named Jonathan Ross. And he was there. He designed them in a dialect of this little language you might have heard of called Haskell. So TPUs were designed in BlueSpec, and BlueSpec started out as a Haskell compiler. Again, the tie back to first Haskell talk I ever gave was in BlueSpec's offices. And so Jonathan designed TPU v0 or whatever in BlueSpec, and they made him rewrite it in System Verilog. And then they brought in a bunch of traditional hardware folks, and it went from getting like, when it was originally just done on FPGAs, he was getting like 70% utilization of all the DSPs and whatever the theoretical performance top of the chip. And kind of everyone expected it to be 35%. They brought in all the traditional hardware folks, and guess what? It plummeted to exactly what you would expect. And then they shipped it. So he got very kind of upset and frustrated by this process and left and formed Groq. So Groq makes a big neural network accelerator chip. I think it's the largest single core SIMD. Like it was literally the first single core architecture to do a petaflop in one chip. So it's a gigantic SIMD unit. And I've given talks on how to compile like functional languages for SIMD style architectures. And I still am a big proponent of this because, again, if I dip into my sort of AI safety kind of like my toolbox there, I'd be much happier if like a lot of the deterministic stuff just worked at scale on the kind of hardware that's kind of creating the problem. Like if I could use the stuff that I can reason about at scale, but if the stuff that I can reason about is only scaling so fast and TPUs and GPUs and all this kind of stuff are scaling off to the side here, then the space of things that I can reason about those systems doing is much smaller than the space of things that those things can do. So I'd much prefer this, like the systems that I can reason about, to scale with the kinds of things that I think are creating the problems. So I wound up at MIRI doing a lot of research on, what does it take to get functional programming, logic programming, and formal methods to scale, and like trying to figure out how to do that on GPUs or SIMD units on my CPU. I can't even keep the SIMD unit in this little Mac over here hot with Haskell, let alone like my GPU in the other room, let alone some TPU in the cloud. And then really, I kind of got as far as I could go using like what was available to me in terms of off-the-shelf documentation. So I got involved with Groq, helping them out like just a day a week or whatever as a consultant. Jonathan reached out to me kind of cold through Satnam Singh and some other folks, and it just worked out to be a really good mental fit. And then last summer, I left MIRI and joined Groq full-time as a fellow, looked around, realized they needed some help on the software side, and just took over as head of software. So now we have a large cross-section of models compiling kind of fully automatically from PyTorch and TensorFlow all the way through to the chip. You can basically take machine learning models off the shelf. As we start supporting more and more operations, it just more and more things just work. And we make reasonably heavy use of Haskell in the tool chain. It's not everywhere. We have a Haskell-based assembler. We have like the visualization tools are in Haskell. Our infrastructure is all Nix and Haskell. But like the compiler itself is a big MLAR, C++ kind of thing, right? And some of the user experience stuff is all often Python and API tools and stuff like that for building programs that can run on our chip. And so you've got different ways of interacting. Like you can go either the fully magical route through the compiler or through this Groq API if you're willing to hand write for the architecture to try and get every little last erg of power out of the chip. And then the chip is designed to be this, like, not just a completely deterministic chip, but it's designed that you can build a network of these completely deterministic chips and have the result be completely deterministic.
Yeah, that's actually what I wanted to say. Like, what I wanted to ask, how do you actually make them into something more fun than just
so let's
one
just
model?
Look at one chip for just a brief second, right? And what I'll do is and apologies for the people following along at home. Basically what we have is on the sides of the chip, there are these matrix multiply units. And these can do like a 320 by 320 matrix vector multiply every tick. So every clock cycle, I can start one, and they're fully pipelined, so I can retire one per clock. And I actually have like two of them on each side of the chip. So I can do two 320 by 320 matrix multiplies per side of the chip per clock. I mean, these are like int8s, but you can still do an awful lot of matrix matmults on this chip. And then there's some shuffle units. The shuffle units on the inside of that move data up and down the chip. And then you have a lot of memory. And the idea is that data moves left or right to left on streams that only kind of move laterally, east to west or west to east. You got like 32 streams worth of data going in each of those directions. And every step, every tick, the data is moving one step down the stream. And so each one of these functional units, like each one of these slices of memory or the MXM or whatever you've got here, its instructions are locally very simple. Take whatever's on the stream and multiply it, or load new weights into the matrix multiplication, like for the weights, and then you're going to do more activations on subsequent clocks, or write this to this address, or something like that. They're very simple instructions on a per functional unit kind of basis. But what you do is you orchestrate this entire program because you can see the entire program in advance. And there's no caches involved in the mix. And so in a normal CPU, like 30 or 40% of your chip is probably taken up by caching logic. And that caching logic isn't contributing to your top line TOPS numbers. It's just boilerplate to turn around and try and make some things a little bit faster situationally. So what's happening here is I know exactly when something's going to happen. So I can just read from it. I don't have to have any control logic come along with the data to say, oh, please start now. Now we start saying, well, how do these communicate with each other? Well, I have another chip off to the side here. and I can send data over one of these chip-to-chip links, and it just shows up 600 clocks later over like this QSIP link or whatever. And it looks, as long as I get these clocks between these two chips synced close enough, and they drift at maybe 50 parts per million or something like that. So as long as I keep those clocks in plesiochronous sync, this looks like, and I just do a little bit of buffering at the end, so the error bars are like, instead of being 550 at the low end, it's 600. Then this just looks like a deterministic network message. I just send a thing from here to the other chip. Now I'd have to normally deal with, hey, look, I got it, ACK. And instead of doing ACKs, what we just do is we do forward error correction on the link. That's why it's 600 instead of 200 or something like that. We have to do all the forward error correction encoding. And that lets us bring mean time between failure up high enough that we just don't need to practically worry about it as a concern while running programs up to exascale kind of computing. We just like, you run the program and the odds of it going wrong are so low that like you just rerun the program when it goes wrong and you get all the error correction, you get all the error detection bits out of the FEC machinery. And so forward error correction plus doing this sync for plesiosynchronous networking means that in theory, I could take a Groq chip V1 and take 10,400 of them and get them into one gigantic synchronous fabric. And it would look like one big deterministic computer, keeping in mind that each one of those is almost a petaflop.
Wow, that's cool.
Right. That is what like the V1, like the silicon that we have today, was designed to facilitate. Now in practice, are you going to go past 2-4 racks? Probably not right now. And we do have a next generation worth of silicon coming, which kind of changes the scaling story even further. But this, if you look at this chip, all this memory here is SRAM. There are like 220 megabytes worth of SRAM just sitting there in the middle of that chip. And so the SRAM here and this big vector processing unit in the middle I didn't talk about, which is basically like configurable. It looks like 16 ALUs to you for each lane because there's like 320 streams worth of data. So if you think about this in SIMD terms, like on my CPU here, I got a 256-bit SIMD unit. Or maybe it's 128 bits because this is Apple Silicon over here, but whatever. On that, it's 320 bytes. So there's an order of magnitude involved in the difference in size for SIMD. But then all the memory is structured to read and write in that fashion. And the shuffling units and the C to C.
Can you do? So, I mean, I don't think you need it right now, but like, is it 2-dimensional racks, or can you do actual like 3D stuff, like linking your CPUs vertically as well as horizontally?
So the way we link the chips is in a Dragonfly topology. So like within a node, which is 8 chips, they're fully connected. And then when you start getting beyond the node scale, we start drifting into something that looks a little more hypercubish, which is what a Dragonfly is.
Okay.
The way we kind of structure things. So we use a Dragonfly topology because it gives us the general best cross-sectional bandwidth that we can get for that kind of system at scale.
Nice.
And then right now you can basically, I think as of today, I can turn around and get a Groq API program to run at rack scale, and then a compiler program, like we've got a couple of examples that are running at a couple of nodes. So 16 chip scale.
Nice.
As we work on improving the performance of the assembler and the FFI process between the C++ based compiler and the Haskell based assembler, because that was previously a separate process, we just throw a big file over the fence too. Now it's being FFI'd into from the C++ program. And that rather drastically reduces our communication overhead and lets us give feedback to the compiler and make compiling more robust. As that's coming along and we're improving the performance of that interop, we should be able to get the compiler up to full stuff to be able to compile for these larger and larger systems.
How do you, very briefly, manufacture those? Because it's, for me, with the previous success of Intel, I didn't even, I'm a completely external observer for this, right? Like I never worked with hardware. I didn't even burn a house or a flat down ever. So, so like for me, I saw there was some two competing three competing architectures, right? There was like a RISC architecture in Sparks, and then there was two like I don't remember, CISC, right? Architectures in AMD and Intel, and they were kind of competing, and then Intel won. And then I was like, wow, that proves the fact that chip design is completely undemocratic, and that's gonna be a monopoly forever. And then, well, we know what happened then we got FPGAs, then we got
Intel had some famous problems with their fabs. There's a bunch of things that went wrong with their process. And that opened up the room for everybody else to kind of sneak into the market, and for AMD to stay alive for a while and all that.
Right. But these days, it's still, the field doesn't feel too democratic, if you know what I mean. So like, I wonder, how do you do manufacturing? How did this person who made like an amazing chip, right, then said, okay, I'm gonna build my own chip factory with the card games.
We don't have our own chip stuff. We don't fab our own chips, right? V1's done through Global Foundries, and that keeps us like pretty much with a domestic pipeline, which I think makes the U.S. government kind of customers happier. Because I think almost everything in our existing manufacturing pipeline happens in the U.S. or Canada. I think one verification step, we tend to send stuff off to Germany, but we could skip that if we needed to for V1. And so I think that just kind of worked out in our favor. It also meant that while a lot of folks have been dealing with a chip shortage, we have the ability to ship chips right now. That's a little mollified now by the crypto crash has put a whole lot of GPUs on the market. They've been kind of hard ridden and put away wet, but they are at least GPUs that you can buy if you need to do a bunch of machine learning workloads and don't mind the fact that they'll probably have blown memory modules or whatever awful things you're going to get from a thing that's been living and like hand disassembled and mangled and put back together and put into the random Chinese coin mining warehouse somewhere. But I don't know. There's the fact that we have a usable supply chain has been quite instrumental in us like getting customers this last quarter or so.
All right. Well, to backtrack, you started saying, well, I asked about like the analogy fallacy, right? You were saying you were telling some story about experiencing that in your practice, and then we
and
then we drifted into talking about chips.
Yeah, that one's going to be tough. I'm trying to figure out like what I can say that doesn't like explicitly out somebody.
I mean, we can just say it exists, right?
I'll just say it exists. That's when I'd revisit in a future conversation at some point in time or over beers.
All right. Well, I think that just by the clock we should wrap it up. Obviously, it's for me it's a huge privilege and joy to talk to you. I think I could do it infinitely. But yeah, I think we should kind of wrap it up. So I have like a couple of like rapid questions.
Sure.
If you were to discover something today that's not Haskell, what would you discover and be excited about it?
Language-wise?
Yeah, language-wise, yeah.
I mean, I actually still enjoy Rust. Not for cargo culting, going off and writing Rust because everyone's writing Rust, but because like if I look around in the Rust ecosystem, there's a number of things that they pay attention to that like Haskell doesn't. And Haskell can't because of some of the like restrictions on like the nature of the different languages, right? Like I adore the fact that Rust variants are careful about tracking quote unquote niches in their data types, right? Like if you have a reference to a thing and you go to take an option of that reference, the fact that references can't be null means that the compiler is smart enough to figure out that, oh, I can jam the option of a reference into the same space as the original reference and just take over the zero case, right? And so the abstraction of putting a maybe there doesn't have a cost for that data type. And the nice thing about it is this works in general for small variants. And so if I have something like I take an option of a thing that was like 3 different cases, I just get something that has 4 cases in it. And if I take an option of another thing, then I like, oh gosh, I've got 5 cases. And it's just still cramming it into the same byte or whatever it was going to use to store that data. And that's adorable to me. Like the fact that it just does that and it like doesn't like put any preamble or prologue on that, it just happens, is amazing. Or like, you know, when I think about building a compiler, there's a talk by Anders Hallsberg and folks on like, what do you need to like build a modern compiler architecture? And it's really about like building sort of like query-based structures so that you can ask it questions and like it can recompute. And in the Rust ecosystem, the Rust compiler is built on top of something called Salsa, which is this project from Nico Matsikis, I think, which is very similar to a little Haskell library called Watch, which implements much the same idea. And Ollie Fredrickson and Haskell has something called Make, which also implements the same idea. And we have Shake in the Haskell ecosystem, which implements much the same idea. Each one of these things is sort of the same idea, like being groped at from different directions. But I think like they really exploit like Rust's macro system to make it just pleasant to use. It just feels very rusty to write code to use this sort of abstraction layer that is dealing with all of the lazy recomputation in the presence of changed inputs. And those kinds of things. Like if I'm trying to write a compiler in Rust, well, what would I do? I'd probably take tree sitter, like build the thing to like lazily to recompute as my syntax tree changes. Like use the fact that I've got Tower LSP to directly build the language server protocol. Absolutely could use the LSP package to do that in Haskell, but it's still another thing. And then I would use something like Salsa to manage the internals of it. And then I'm just focusing in on the pieces that are left over that I care about. Like all of the boilerplate's been taken away from me. And the fact that those libraries largely fit together in that ecosystem really appeals. I realize this is a very long-winded answer to a throwaway, quick, where would I have to go to get excited? So that's my workman-like answer. Like if I put on my industrial Haskell hat, that's my answer. If I put on my more theoretical Haskell hat, the main direction I was kind of going when I was working at Miri was around like, what does it take to build how do I make functional programming scale? And my sort of answer is like, how do I make a dependently typed language that takes type classes, as Haskell calls type classes, seriously, in the sense of my type classes versus the world rant, which is another talk that I've given at some point in time that people love or hate. Apparently, it somehow indirectly led to Rust's traits. So I'm very happy that I gave the rant. But it's why do I care about that? So I was working on this programming language project called Coda, which is how do I make dependently typed programming that takes type classes seriously, where they actually mean what Haskell programmers say when they think about type classes, the category constraints is thin, or at least that's the way I think of it. Or like basically Lavier theories or essentially algebraic theories or whatever you want to call them in this particular framework. And if I start going there, I start like heading down towards like a road towards like an extensional type theory that is mostly syntax directed, but where I can offer a little bit of help and where each one of those residual problems that I get out of the type checking process becomes something that I sort of discharge almost through like Cox obligation tactic or something like that. And that's an awful lot of words. But the point of it is, how do I make something that like feels like Haskell to program in, and that I could then incrementally refine until I get the confidence that I can have in like an Agda or a Cox style program, but not stop the user at every step along the way, making sure that they've juggled getting the types right and all of this kind of stuff in just the right order in order to build the perfect program all in one go. Because you just have to hold too many things in your head. It's like in Rust, I have to fight with the borrow checker all the damn time. Like even before I can even start to think like the thoughts of my algorithm. And now eventually you get used to wearing that straitjacket and it doesn't confine you. You know, you just don't move the wrong way. But and in Agda and Coq, you get used to it as well. But like, how can I make the sort of big moves that I can make in Haskell and still eventually get to that confidence that I really want?
What you're describing is something that so Lean 4 has functional dependencies, right?
Lean gets so close to a lot of what I want.
Yeah.
And we could go into a very long, detailed rant about what's good and what's bad about Lean from my perspective.
Well, what's bad about Lean? Because we have a lot of Microsoft research.
I don't know that I want to pick this fight because Leo is smarter than I am on almost every dimension. And I say that with like all due candor.
What don't you like about Lean? Let's put it
Oh
like
gosh, there's a lot to like about Lean. And I realize I'm being very complimentary at the moment. I was just being mildly antagonistic. The notion of what Lean calls, like, what Lean's notion of a type class or implicit or whatever, kind of follows the same pattern of everybody else in the space. Like if you look at Coq or Agda or Adrian, basically they start looking around and they say, okay, well, we had to add some kind of pattern unifier to our type system in order to get to make it usable. So they start off with like they can't do full higher order unification because like you can only come up with a semi-decision procedure for it. So Hewitt's algorithm or whatever will just go forever. So then they all go off and they fall down to Miller's pattern fragment, which is basically, hey, look, like if I need to like do unification on lambdas, I can do it, but only under certain conditions about like what you're doing with the arguments. Okay. But then they say, okay, now I've got this pattern unifier. Oh gosh, if I was looking for a dictionary for eq and I had one lying around for ord, I could mangle it into that using one of these rules that I happen to have lying around. Right now I do that in Coq. I realize I'm rambling on about Coq, not about Lean in the moment. I'm just using it because it's a little more illustrative. Then what happens is there's like one blessed path through these coercions that's allowed to get from any one thing to another. But if you ever have to kind of go this way, there's nothing that actually says that this little diamond is coherent because these are arbitrary functions. They can coerce anything into anything. They're just kind of bolted into your pattern unifier. And as a result of that, I don't know that I can really say an awful lot about type classes or implicits or whatever in a world like that. What I really want is a category of constraints that is thin, that like any of my paths do commute, and the use of them kind of is contingent on that fact. And so putting a few syntactic restrictions on like what you can use through the class mechanism that brings it closer to what Haskell offers you, A, is very appealing to me, and B, also turns on to be like effectively a extensional type theory, which is one of the things that drives the whole system. We want to be an extensional type theory rather than a traditional intentional type theory. And like going into what that is and exactly what that means and why one would care, I think would blow your time budget by a lot.
Well, I mean, I hope that our listeners will have a lot of fun kind of reading the references, and me and our producers will have a lot of fun building the list of references for this one.
So I will confess, I did not actually get around to finishing Coda. I went off and did a little project called Cadenza, which was me trying to see whether I could write an interpreter for functional languages that would run efficiently on Truffle and Groq, which are, I've given a talk or two on Cadenza. You can probably dig up. And in music, the cadenza happens right before the coda. It is a little virtuosic solo project. Didn't turn out to be a solo project, so I wound up working with somebody on it. But the idea was originally there. Why was it what cadenza itself wound up kind of helping to inspire the work that what used to be Luna Lang turned into ENSO. And so I've been doing some work like helping out the ENSO folks to try and figure out like what a type system would look like for their language. That's a not lazy, but mostly functional style language. It's running on the JVM using the polyglot machinery for Truffle and Groq to kind of like, I don't know, let it basically raid other languages for parts. Gosh, it'd be nice to be able to use NumPy. Oh, I guess I can, because it can just use Python through Truffle. And then it JITs, so it actually tends to run better than you're going to get out of stock Python. So being able to rate other languages for their best of breed libraries and stitch them all together in kind of a functional fabric is kind of an impressive little toy to me. So Coda morphed into the Cadenza side project, and then there's this enso.org project that is kind of picking up and running with that particular dream. And I've been helping them out where I can in my copious amounts of spare time.
I mean, I guess my last question, since we started talking about all the different programming languages, what are your thoughts on ATS?
ATS is almost really interesting. The syntax of ATS T at YPE or whatever. I can't quite remember the idiom there, and what have you. Make it really freaking hard to use. It's like, who's it? Victor Taylor's work on Candelia or whatever. Like, it's so close to something that I would want to like just run around with, but it's so hard. I don't know if you've tried using ATS in anger at all.
Oh, not in anger, no. But yeah, for my feedback is the same, except I'm like 10 times less smart. So if your feedback is also that it's close to something that
it's fast, and like Hongwei's put a lot of work into it. Like trying to make something that basically has no overhead. Don't get me wrong, but
no, it's a wonderful bit of engineering, and I almost want to say language design, but then compiler design.
If you just chose random names for things, I think you would do better than the conscious choices that were made by the author. And I don't know how to articulate that well, but it's a good idea and a solid implementation with a very bad skin.
Oh, actually, speaking of absolute for sure last question, because actually I asked my my colleagues, do you have anything you would like to ask Edward? And and I incorporated obviously a lot of the stuff into my questions, but one question kind of stood out to me as something marginal but funny. Like so the question was, how do category theorists pick names for stuff? and additionally, do they still name things? I think that the latter bit is funnier, right? Like we're scared of more things to. I mean,
there aren't like like category theorists will gosh, that's Cartesian whatever, blah blah blah. You got a handful of names that have like largely been selected, right? But then you go off into set theory, and set theorists will just call something a mouse.
Yeah,
it's just a mouse. Why? Because it's a mouse. Like I don't know. Like category theorists are not the most egregious of namers or something like that here. Who was it? Was it May who named the operads and monads? Like they used to be called standard triples. That's what a monad used to be, or whatever, back in the day. And then is it J.P. May? I might be wrong. Suggested that because I guess apocryphally, because his mother was an opera singer, he wanted it, like thought about it and named operads, and then like monads, so they would go with operad. Therefore, like this thing about operations would very nicely coincide with this thing on general operation. So there's some naming that's going on there. There's always an art to it, obviously, but I don't know. A lot of it is Grothendieck named everything, and so you just use his names and maybe sometimes mingle some things out of French.
Nice. That's
distributors, profunctors, modules. There's like a handful of different names for profunctors as an example.
Yeah, well, I mean, we all know what they say, that naming is the most difficult problem in everything and programming.
I name by puns. I'm not even a category theorist. I'm just, like I pretend like in a crowd of Haskellers, maybe I look like one, but I am not. I'm a terrible category theorist. And so I name entirely by puns. My naming sense was more or less stolen from Connor McBride's papers.
Joker, clown, yeah.
Clowns and jokers and, let me be and all these different little like puns and stuff like that. They're just sitting in all of his data types. So like when I started naming things in Lens, we were just having fun. Like a lot of these weird names for cars and stores and stuff like that came out of just like wanting to continue a theme.
Nice. I think it's pretty intellectually honest, because then it kind of drops the pretense, right?
I will say this. I very much believe in using the right name for a thing. And I think that this came up in that talk that you mentioned earlier. which is that, like if I use the proper name for a thing like that, like which has references back into the 60s, 70s, 30s, wherever the hell it was, then what happens is once I've written down a piece of code, someone can tell me something about my code that I didn't put into it. Right? I say, hey, look, this is just a right semi-nearing or something like that. And then people can come out of the woodwork to tell me, no, actually, and then I can learn something. But if I just say, oh, this is an addable something, or an appendable, whatever, and that's monoid, and I just didn't use the right name, then no one will ever think to tell me whatever it is. And if people Google for my whatever I talked about, they won't find any resources that, unless they happen to already know how to make that connection. And I think consistency matters for names a lot. And there are places where I do I tried to muck with convention. Like we had CoState for store. And I rather deliberately, when I was making the Kmetts library in Haskell, picked names for the co-foos. Partially because I didn't really feel like they didn't feel like the co anything until I found that co construction that's buried in the Con extensions package, which converts one into the other. But then there was always the question of, is co-reader related to reader or is it writer because it looks like writer? And is co-writer, is that reader? Is, you know what I mean? So giving them the other, like another name, like disabled this twisting that was in everybody's brain and let people start finding some intuitions for how to actually freaking use the Kmetts in practice. Right? I think like the articles that I have buried on like School of Haskell that go into, and here's how we're going to use a Kmett to solve this particular problem. Like, I think are probably the only things that really talk about using Kmetts to solve problems on the internet. I mean, maybe you've got some stuff that
there is the UI, the whole studies in UI by PAF31 by the author of PureScript.
Yeah, I was going to say the PureScript guy has a whole like thing on like using day convolution of Kmetts, and that's about it. And now we're starting to see this, like Kmetts give rise to a category in Poly and all this kind of stuff. So, or just in general. And so you can start using them as a vocabulary for that kind of work. But it's a very different way than people think about like using monads to organize a program.
I know that you well, like, okay, we are living in like TikTok generation and Twitter generation, etc. Right? So people want to get the answers to their questions quickly.
Mm-hmm.
So I have this problem myself sometimes. I do something like that has a certain shape, and I know that there is a name for it. I like 99% certain there is a name for it, but I know I don't know it. So what I do is I go to Google and I hope that you wrote a library from which I can steal the name or just use your library, right?
Mm-hmm.
But maybe there is a better way than
just randomly taking whatever library happens to have my name on it as an endorsement.
No, I mean, but you know what I mean, right? Like sometimes you have a shape and you know that it's there is a proper name for it, right?
Mm-hmm.
And you would like to use it or use a library that already implements it in a composable way, right? Is there a way, except for hoping for Google search?
I mean, there's like the type Classopedia, which never really got updated with all of the other divisible, decidable kind of machinery and stuff like that, right? Like Brent Yorgi's old type Classopedia was like a real eye opener for me at the time because he was writing it, I think, right at the time that I was getting ready to like go nuts with category extras. I've forgotten exactly the timeline. And then like from a category theorist kind of perspective, there's the Baez and Stay paper on the Rosetta Stone paper that they have, which is a good sort of like tour of why do I care about these different kinds of braided, monoidal, blah, 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 whatever the kind of categories. And so like those are, I think, maybe your best choice of entry into like, what is the name of X, Y, or Z? And I think it's very, how to put this? Category theory for me is a good source of questions or observations I can make about a domain. Once I know that something is a, fill in the blank XYZ kind of category, I know an awful lot about it, right? Like you can learn an awful lot about quantum computation just by observing, its particular structure and, as a Dagger category of with this kind of structure and that kind of structure. And I think that tool is something that isn't sold well enough to the general population. I mean, people say, oh, well, category theory is just like Rosetta Stone, this bridge for moving back and forth between things. But it's really helped my ability to just Google for a thing. Because I do that same thing, but I do it for papers. I try to read papers by inventing how I would do a thing, trying to put it in math words, and then Googling for the math words that I chose and the discipline or whatever, and then reading whatever paper comes up that's usually 20 years old, 30 years old, and then taking that almost as if I got the result of my experiment, and then thinking, like, maybe picking a fight with it, like ripping apart one of its invariants and seeing, like, reading it very critically, and then using that as to kind of inform the result of my experiment to say, okay, well, now what would I do with this updated belief? That'll usually jump me a year or two in advance. And by the time I'm done, I'm usually close to current in whatever discipline I'm trying it in. It's this having the math there is very useful for being able to climb that paper ladder, because otherwise you have to have somebody else who knows all the papers.
Yeah. Well, that wraps it up. Thank you very much. And I hope that your work in Toppos Institute will help people from TikTok generation to find the correct abstractions quicker, perhaps. Maybe there's a startup in it, right? Like abstract to go.
I mean, like it's just doing what I do and like just reading random NLab pages and then turning around and trying to write them out in Haskell. Maybe isn't the most scalable approach for everybody on the planet to try, but it was quite useful for me. I think an old Neil Ghani paper on, this is obviously a left con extension, and squinting at it and looking back and forth between that and the Wikipedia page, and eventually getting, that's what a left con extension is. Wasn't necessarily the on-road that other people should take.
Well, thank you very much. If you ever have, in your myriads of spare days to drop by and chat with us about whatever you want, we will welcome you with open hands.
Well, thank you for having me. This has been a lot of fun. I apologize for quite how long it took to get this on our respective calendars. I think you reached out to me maybe 6 months ago. And I appreciate and applaud your patience.
It's our pleasure. Thank you.
All right. Thank you.